Welcome back. Uh, Today I'm going to discuss about tensor notations that we need to use in the study of fluid dynamics. So let's get started by considering a vector A. So normally we would write a vector in a column. So I'm going to consider it has three components. Okay. And those three components, instead of writing that column, I can rewrite that a sub I, and I will imagine this index I is going from 1, 2 and 3. Okay, so this is called a free index. So we can use an index and use that index to denote a vector. So for example, if I have a vector x, I will write it using xi. Good enough. What is a free index and how do I denote a vector? And now let's say we want to do a dot product. Okay. Dot product between a and x. So we know that the dot product is a1 x1 plus a2 x2 plus a3 x3. Okay. So we can write that in short form, sum over I from 1 to 3 ai xi. And here is something that I have to do a dot product a number of times when I'm studying fluid. And I don't want to write this sum every time I write a dot product. So I will just write ai xi. And I'll make a convention here that I will say if I have a product and if there are two indices and if those indices are the same, then I will imagine that is a sum. So I'll say, okay, sum over repeated index, sum over repeated index. So if an index is repeated, I will take a sum. And since I forgot these summations, I have to blame someone. So I'll pick a scientist. I don't want to blame a fluid dynamicist, so or any other physicist. Newton, Kolmogorov, Taylor, they are doing fluid. So I will pick Einstein. Let's say, okay, Einstein forgot this, and we call this is Einstein's relation. So blaming someone sometimes is a good idea. That helps. Okay. So having said that this is a dot product, let's try to think of how we write the gradient. So the gradient of a scalar quantity. So let's say gradient of f. So gradient of f is written as partial f with respect to x, partial f with respect to y, partial f with respect to z. Okay, so and this one we'll just write partial f xi. So I have a free index, free index I, and that means partial f with respect to x with a free index. So it has three components. I'll have to differentiate f 3 times independently. So what we are doing here is straightforward. In tensor notation, we don't have to look at those matrices. I will take the component wise and then differentiate each component with respect to each component of my variable, vector variable that I intend to differentiate with respect to. The only thing is we have to make another convention. I'm not blaming Einstein, but it could easily be blamed to Einstein. For that is that when you are looking at UI, so let me just write down here. So when you are looking at UI, then that means you are saying U1, U2, U3. So that is the standard notation. Always we say. But now you can see here, when you are differentiating, I'm first taking the differentiation with respect to x, y, and z. And now if I write the derivatives column wise, then I'll fill up the space from here. So I don't have room here, I can't go there. So that is why I take u1. I'm writing the gradient of u1 but writing row wise. Look at back here. I said if I have a scalar f, I take the gradient. I'm writing the gradient is a vector which is column wise, but a vector can be also written in row wise. Here the problem is that I can't write the gradient of u1 column wise because I don't have the room, so I put it in row wise. So this is something I often find students get confused, but there is no confusion. What we will do in tensor notation is that we will write dui dxj, and I is for j, sorry, I is for row, j is for column, I is for row, j is for column, and that makes things easy. Okay, so let's see, take a second break and rethink what we did. We looked at dot product, we looked at gradient of a scalar, then we looked at gradient of a vector. So when I take the gradient of a scalar, I differentiate the scalar with respect to a vector. Now when I take the gradient of a vector, I differentiate with respect to a vector. And that's complicated, and that's not actually complicated if I use tensor notation. So I know my rule of thumb that differentiation of vectors will be element wise or component wise. So if I have a vector, I have to differentiate with respect to another vector, I will do component wise. And when I do the component wise, I use tensor. If I use the tensor notation, even if you are not doing fluid dynamics, for any other subject, you want to differentiate a vector with respect to a vector, use tensor notation. Blame Einstein for forgetting something, and that will be nice. Okay, so at this stage, I think I want to take another break and say something. This is a scalar quantity, and it is written in tensor notation. Let's say df dxj. So it has a physical meaning. So the physical meaning, we can see that we know gradient of f is a vector. So let's say this is a vector, and we know u is a vector. So let's say u is like that. Okay, so u dot gradient of f will be the dot product, and we know that this dot product is a directional derivative. So this one will be called a directional derivative, derivative of f in the direction of u, derivative of f in the direction of u. So in regular calculus, when I take the differentiation, I don't care about the direction. But in vector calculus, or particularly in fluid mechanics or continuum mechanics, I have to take derivatives in vector quantities. So I have to define something special, that is rate of change of f in the direction of u. Okay, so good enough. I just took a break by talking about this directional derivative, and let's come back to tensor. Okay, so I will first denote two special tensor. So the first one is delta ij. So this is just 1 or 0. So it will be 1 if I equals j, and 0 if I is not equal to 0. Okay. So forget the name, what is the Kronecker delta or Dirac delta. It's a delta ij. So this is delta ij is 1 or 0. So this will be, if you write in the matrix, this will be a diagonal matrix. This we know it. Now I'll go back for another one, epsilon ijk. This one is a bit complicated. So its values are 0, 1, but it could be positive or negative. So that means it could be -1, 0, or 1. So the question is, when I take 0 and when I take -1, and how do I know? So to do that, we will first define a order, and these days little not very difficult because we don't have the clock. We all have a phone where we can see, a computer where we can see the time, but we still understand what is a clock, and the clock moves in a direction. Clock moves in a direction. So I'll think that I'm moving against the clock. So I want to go against time. So I have I here, and I'll put j here, and then I will put k here. So if I go I to j and j to k and k to j, okay, so that will be against the clock. So I'll say counterclockwise. So always epsilon ijk will be counterclockwise. So if I switch the order, so let's say instead of ijk, if I say ikj, so let's write that here, epsilon ikj. Okay, so what happens? And this is something we know the value. If epsilon ijk is plus, if this is plus, this will be minus. So if you change the order of the index, and those indices are in fluid is 1, 2, 3, and when I use epsilon notation, it is fixed. Epsilon notation, it will be used I for 1, 2, 3, j for 1, 2, 3, k for 1, 2, 3. Okay, so that is the sign. Now the value is 1. So if you change the order of the index is -1. So what is left when it is 0? So it will be 0 when you have a repeated index. And this time I'm not going to blame Einstein. Perhaps Einstein forgot to look into that. So epsilon ik. So 2 indices has been repeated. I don't want to take the sum, but I don't mind to take the sum afterwards. I will first say if I and I repeated, so this is 0. This is neutral. So okay, why it is 0 is because you are not going counterclockwise or you are not going clockwise. I to I, I to I. So you are at I. You are not moving forward. You just in one place. So it's 0. Okay. So if you have epsilon I, j, and j, okay, so that will be 0. Okay, so now what I can say here, I can say, okay, epsilon I, j, k is 1 if you go counterclockwise. So maybe you can use it notation like that. Will be -1 if you go clockwise, and will be 0 repeated. Okay, so let's take a simple exercise. Epsilon 1, 2, 3 equals what? So equals 1. Epsilon 3, 1, 2. So 3, 1, 2, 3, 1, 2, 3, 1 counterclockwise or clockwise. 3, 1, 2 counterclockwise. So this is 1. So now if I say epsilon 3, 2, 1. So this will be -1. So nice thing about that, we can do a lot of other thing. For example, cross product. So this time I'm not going to explain it, rather than I'm going to inform it. So what I'm going to look at here is that I want to know how do I write cross product into tensor notation. So I'll use epsilon I j k, and then I will take the first vector a, put an index I, and second vector b, put an index j. So that will be the cross product. You can write it out, you can verify that, you can take the cross product and then you evaluate that, you will get that. So I leave that as an exercise. Show this. So you know the cross product. Now you have learned the sum of our repeated index. So there are I. So these are repeated index. So you have to sum over that. J, repeated index. You have to sum over that. And k is the free index. So this is a cross product. You know how to do the cross product, and then verify it. Take the left hand side, use your general knowledge on cross product. Take the right hand side, use your tensorial knowledge learned from this lecture, and then say left hand side equal to right hand side. Okay. So let's say I use this to prove something. So we often use the Greek letter rho in fluid mechanics for basically for density. So let's say I have gradient of rho, okay, and then I want to take the curl of the gradient, which is a cross product. And from calculus, we know curl of a gradient is 0, and perhaps we can prove that in different way. But in fluid mechanics, the first thing is we want to see if I can use tensor notation. So in tensor notation, I will say epsilon I j k and gradient. So I will first just write this way. Okay, so a I and b j. So I will write down, go back, I j. I know delta I, which is d x I, and then the gradient of rho, which will be d rho dx j. Okay. The good thing here is that I can do the curl without knowing the determinant and cofactor. Now I have to make something here. So the first thing is this, that is a free index. So there will be free index k. K has 3 values. K is 1, k is 2, k is 3. Okay. So let's say k is 1. So looking at k is 1. So now I have I repeated, so sum over I, j repeated, sum over I. So if I take the sum, I will say epsilon I 1k, epsilon I 2k, and so on. So basically I will get epsilon 1, 2, 1, k is 1. Okay, I'll get epsilon 1, 1, 1. I'm not writing in the sequential order. I will get epsilon 2, 1, 1, and so on. So I cannot take 2 repeated index because they are 0. I will not take. So I will take epsilon 1. Sorry, I cannot take epsilon 1. I will take epsilon 2 and 3, 1, because k is 1. Okay. Let me erase those things. I'll take epsilon now 3, 2, 1. Okay. So epsilon has several components. For k equal to 1, epsilon has 9 components. Okay. I only have two components, and epsilon 2, 3, 1. So we can look at here 2, 3, 1. So going 2, 3, 1 counterclockwise. So this is positive 1. So positive 1 dx 2 d rho dx 3. Okay, and then 3 1 negative 1 d dx 3 d rho dx 2. How about forget tensor? So d dy d rho dz minus d dz d rho d dy. Okay, so for k equal to 1, so this is for k equal to 1. So similarly, I will write for k equal to 2. So that will be I have to think of, let's say this time let's try to be a little gentle and see if we can make it little clear. So k equals 2. So epsilon 2. So I have the option 1, 3, epsilon 2. I have the option 3, 1. So which one I write first? 1, 3 or 3, 1 doesn't matter. So I'll write epsilon 1, 3, 2. So I'm going to think here 1, 2, 3. So 1, 3, 2 will be like that. Okay. So that will be negative. So that will be 1, which is d dx, 3, which is d dz, and the second one is negative d dz d rho dx. Once you write the first one, second one, the first one is negative, second one is positive. Second one you can write it immediately. So similarly, I'll go for k equals 3. Okay, so k equals 3, epsilon, you put here 3, and then you think of, okay, you have the option 1, 2, and epsilon 2, 1, 3. Okay, so 1, 2, 3. So 1 is x, 2 is y. So d dx d rho dy. So this one will be d dy d rho dx. So 1 is positive, 1 is negative. Even if you make a mistake, it's not a problem, but you don't want to make a mistake. So 1, 2, 3 will be positive or negative. 1, 2, 3 counterclockwise, and 2, 1, 3 clockwise. So this is positive, this is negative. Now you see that all those three components, by mixed partial derivative, this is 0. By mixed partial derivative, this is 0. By mixed partial derivative, this is 0. Even if you make a mistake of sign, you know that one of is positive, other is negative, you still get 0. I'm not saying that we can make a mistake, but it's good this way instead of regular method, calculus method. Okay, so the advantage of tensor calculus is that curl of the gradient is 0. Okay, I think this is going to be a long lecture, and I don't want to take too much time, so I want to give you a homework. So using tensor notation, evaluate divergence of a curve. Okay, so perhaps you know divergence of a curve is 0. I'm going to leave it with you to use tensor notation, and I hopefully you will be able to do that, and I will stop here. If you have question, feel free to reach me. We can make another lecture, or I can answer you. Thank you very much.